Good afternoon, everyone. Today I'll be presenting some new results on device-independent QKD, which are based on combining a series of recent improvements in the topic. In fact, I'll be presenting two works today, which were collaborations between quite a number of research groups as shown on the screen here. I'll begin with a quick overview of the setting for device-independent cryptography, which is a Bell test scenario. What happens here is that Alice and Bob have a pair of devices which share a quantum system between them, and then we have an adversary Eve who holds a purification of the quantum state. And in a typical device-independent protocol, Alice and Bob will supply classical inputs to the devices, and based on the values of these classical inputs, the devices will measure the shares of the state that they hold, and they will produce a corresponding output. So Alice and Bob will gather the classical inputs and outputs across many rounds, and they'll use the data that they gathered to perform some statistical estimation. Now, one of the key results in entanglement theory is that if the classical input-output statistics violate a Bell inequality, then this means that the state shared between the devices must be entangled between Alice and Bob. And this is important for QKD because it suggests that there's at least some possibility of generating a secret key using this entangled state. But the interesting thing about this conclusion is that we were able to come to it even without knowing exactly what were the measurements that were being performed by the devices or even the dimensions of the systems that they act on. And this is the viewpoint of device-independent cryptography, where we aim to base the security only on the Bell violation, and this allows us to construct security proofs that do not assume the measurements performed by the devices are exactly characterized. So this gives a higher level of security than standard QKD because we don't necessarily need to trust the measurements fully, although we do still need to impose some minimal assumptions on them. So one of the key benefits offered by DIQKD, as we just mentioned, is that it has a higher level of security compared to standard QKD. In fact, because the security proofs don't rely on knowing what the measurements are, this offers an improved level of resistance against some hacking attacks that have been developed on QKD implementations. On the other hand, the security proofs in this setting are much more challenging because, again, we don't know what the measurements are. And the protocols that we have usually have fairly low noise tolerance compared to the case of standard QKD. The good news is that recently there have been a series of proposals that improve the noise tolerance of DIQKD, and we'll quickly go over a few of them now. Two, actually. The first approach is known as noisy preprocessing, and it's a modification to the basic DIQKD protocol. To get some understanding of how it works, let's look at the asymptotic key rates. Here we have what's called the Davitat-Winter formula for the asymptotic key rates, which is the difference between two entropies. And in this expression, A0 is Alice's key generating measurement, whereas B0 is Bob's key generating measurement. And that means that the first term here is essentially quantifying Eve's uncertainty about Alice's key generating measurement outcome because it's an entropy. And on the other hand, this term here is quantifying Bob's uncertainty about Alice's key generating measurement. So it's kind of intuitive that the difference between these two uncertainties gives you the asymptotic key rate, although actually the full proof would be significantly more complex, of course. But to gain some understanding of why noisy preprocessing is useful, the idea for this modification to the protocol is that Alice will add a small amount of trusted noise to her measurement outcome. And because she's making her outcome noisier, this means that both of these values of entropy will increase. But it turns out that there are some situations where the first term increases more than the second term, and this leads to an overall improvement in the key rate. And that's the idea of noisy preprocessing. This was previously studied in a setting of standard QKD, but last year we published a result showing that you can obtain similar improvements in device-independent QKD as well. So by using noisy preprocessing, you can improve the key rates and the noise tolerance of DIQKD. The other modification that was proposed last year is called the random key measurements approach. So most DIQKD protocols rely on using a specific pair of measurements for key generation. But the idea proposed in this work is that you can randomly use different pairs of measurements for key generation. And in that case, the asymptotic key rate, if we skip over some details, is essentially a weighted average of the key rates for the two situations. And the intuition here is that Eve is not able to attack both of the key generating measurement pairs optimally, and this results in an overall improvement in the key rate. So this work was developed last year as well, and it was shown to improve the overall key rate and noise tolerance of DIQKD as well. Now, for those two results, to quickly summarize some of their key features, one important property for both of them is that they are based on the CHSH inequality, which is one of the most well-studied Bell inequalities. And both of these results eventually showed that Using the existing bell test experiments, it might be possible to achieve the DIQKD in the asymptotic limit of many protocol rounds. So for example, for noisy preprocessing, it seems promising for photonic implementations, whereas for random key measurements, it seems promising for NV center and cold atom implementations. But these results also raise some very natural questions because, first of all, since both of them are based on the CHSH inequality, an important consideration is whether we can go beyond the CHSH inequality and consider other Bell inequalities instead. Another point to consider is that these results that showed the DIQKD might be possible in principle were in the asymptotic limit of arbitrarily large sample size. But this raises the question of whether the DIQKD is still possible after we account for finite size effects. And this is very important when we want to consider a practical implementation or realization of the DIQKD, because the different experimental implementations listed here, they have extremely different sample sizes. So if we want to compare them, we should do a finite size analysis as well. Another interesting question is that since those two works studied their protocol modifications separately, these variant protocols, this raises the question of whether we can combine them together in order to achieve even better performance in the DIQKD. So in today's talk, I'll present our results that we derived in attempting to address these questions. At the end of the talk, I'll also mention a couple of extremely recent results just from a couple of months ago, which are very relevant to this topic. But for the time being, I'll list our contributions, which are in these two works, as in these two works are what I'll be presenting in this talk. So the first work is essentially based on going beyond CHSH by considering a generalized version of the CHSH inequality. And it also incorporates noisy preprocessing as well, although not the random key measurements technique. I should mention that while we were working on this topic, there was a preprint uploaded to arXiv that had essentially the same goal and arrived at results that were very similar as well. On the other hand, the proof techniques that they used were very different, and their approach is much more efficient on some aspects. So definitely you should take a look at their work as well. The second work that I'm presenting today is based on the idea that we want to combine all the different variations that have been proposed so far to see how far we can improve the key rates with them. And our contribution here is that we develop a numerical algorithm that computes the key rates for protocols that combine all of the variations. Using this algorithm, we prove a new noise tolerance threshold, at least for some simplified noise models. Additionally, since the results suggest that the DIQKD is possible in the asymptotic limit, we also perform a finite size analysis and we compare it to the existing bell test implementations to see how well it performs. So a quick overview of the structure of the talk today. For the first part, I'll describe our results regarding the asymptotic key rates. So in the first work, we consider inequalities other than CHSH and incorporate noisy preprocessing. In the second work, we want to combine all the different variations that have been proposed so far. Using this combination of the variants, we prove a new noise tolerance threshold for the noise model of depolarizing noise. And then we move on to the second part of the talk, which is the finite size analysis. Here, I'll briefly describe some of the technical contributions that we had regarding the finite size analysis, and then I'll consider the results in light of the existing bell test performance and see what the prospects are for the DIQKD in those experiments. And then I'll sum up by describing some of the possible outlook for the DIQKD in the future, as well as the very recent results that came out a couple of months ago. So for the first part, we'll describe the asymptotic key rates. To gain an understanding of this setting, let's first recall that typically in most QKD and DIQKD protocols, there will be a parameter estimation step where the honest parties estimate some parameters of their devices. And then the honest parties will abort if their estimated values are outside of some acceptable range. So for example, for the DIQKD, they'll try and estimate the CHSH value produced by the devices, for example, in the basic protocol, and they'll abort if the CHSH value is not high enough. So if we also recall that the asymptotic key rate for QKD and DIQKD is essentially given by the Davidoff-Winter expression, then we see that the main task of a security proof where we want to compute the asymptotic key rate is that essentially we need to find a lower bound on this quantity over all the possible states and measurements that are accepted during the parameter estimation step of the protocol. So in some sense, we're considering the worst case possible value of the key rate out of all the possible states and measurements that are accepted. So this is somewhat trickier to analyze compared to standard QKD because first of all, we have to minimize it over the measurements as well, because in the DIQKD, we don't assume that the measurements are characterized. whereas in standard QKD, we only need to minimize over the states. And typically in DIQKD, an additional challenge is that we have to consider systems of arbitrary dimension. But for the purpose of the two works I'm presenting today, we focus on the two input, two output scenario, as in Bell inequalities that only have two inputs and two outputs. In that case, there's a sort of qubit reduction in the security analysis, in the sense that more or less it suffices to consider classical mixtures of qubit systems when performing the security proof. Although I won't dwell too much on the details here, but essentially it suffices to consider qubit systems, which simplifies matters a lot. And so in the first work I'm presenting today, we consider a generalized form of the CHSH inequality, and which is shown on the screen here. So essentially the protocol is based on estimating the value of this parameter, and if it's not sufficiently high, then the protocol will abort. We can see that this parameter here is essentially a generalization of the CHSH value, because CHSH corresponds to the case where these coefficients are equal to each other. So it's just a more general expression. And another perspective we can take on this expression is that we can think of the protocol as in fact estimating two different parameters, two different statistics, the ones that are highlighted in the boxes here. And then the security proof essentially uses the optimal linear combination of these parameters in order to derive a bound on the key rate. We do have some results regarding what is the optimal choice of the coefficients in front of these two parameters for a given pair of values. So this is another way that you can think of the results of this work. And to quickly sum up the theoretical results that we obtain, they can be divided into two regimes in some sense. The first regime is a particular range of values for these coefficients. And in this regime, we were able to derive a closed form expression for the key rate. So this is easy to use and when computing the key rates based on a particular combination of coefficients. On the other hand, for the other regime, we were not able to derive a closed form result, and here instead we use a numerical approach. Although I want to highlight that the numerical approach we use in this regime is based on a continuity bound that we derived, and to the best of our knowledge, it seems to be a novel result, so it might be of independent interest as well. Regarding the other work that was working on the same topic, I should mention that they were also able to consider the situation in these two regimes. And in the first regime, they also derive the same expression in closed form for the key rate. For the second regime, however, their approach is much more efficient than ours. And as mentioned previously, their proof technique is very different. So you should take a look at their results as well. But moving ahead to what happens when we apply our results to specific experimental models, let's take a look at, for example, a photonic SPDC source. And here we have plotted the asymptotic key rates given by our results as a function of the detection efficiency. So we take detectors that have limited finite detection efficiency. And you can see here the key rates that are obtained based only on the standard CHSH expression versus our new results from the tilted CHSH expression. We can see that overall, using the tilted CHSH inequality definitely improves the key rates. On the other hand, if we ask the question of where the key rates go to zero, in some sense, the threshold of noise tolerance for this protocol, we see that we find that it's actually quite similar between the two cases. It's approximately 82.6%, although it's not very visually clear from this graph, but that's essentially where the two graphs here intersect the horizontal axis. So by using the tilted CHSH inequality, we can improve the key rate compared to standard CHSH, but the threshold at which it goes to zero seems to remain quite similar. We'll now move on to the second work that I was describing. And in this work, the idea was that we wanted to compute the asymptotic key rates for protocols that combine all of the different variations that have been proposed so far. So by using noisy preprocessing, random key measurements, and the full set of observed statistics by the honest parties. And if we recall that our task in this security proof is essentially to minimize this expression over all the states and measurements that are accepted in the protocol, we see that this could get pretty challenging if we are going to combine all the different variations that have been proposed so far. At least it's going to be challenging to try and find a closed form expression for it. So our approach in this work was that we wanted to derive a numerical approach, but the key criterion was that it had to be reliable in the sense that it always gives a safe lower bound on the key rate, so to speak. We want to make sure that any result we obtain from our algorithm doesn't overestimate the key rate. It's always a safe lower bound. Although, on the other hand, we can also show that our approach eventually does converge to a tight bound, so it won't underestimate the key rate by too much either. I won't go into the details of the approach, but essentially the idea is that if we recall there's minimizations over the states and measurements, well, the minimization over states is essentially the same as in standard QKD. So this is already solved in an earlier work, and we basically took their same numerical approach as well. On the other hand, for the minimization over measurements, we made use of the continuity bound that I previously mentioned, along with several other techniques. But we'll just move on directly to the results we obtained from this algorithm for some noise models. So first of all, let's consider the simple noise model of depolarizing noise. And the results that we obtained in this work are highlighted in this box here. You can see that by combining all the different variations and using the algorithm we developed, we proved that the depolarizing noise threshold for DIQKD can be improved up to 9.33%, which is a substantial improvement over all the previous noise tolerances, including for the protocols that use the protocol variations independently on their own. So by combining them, we achieve a higher level of noise tolerance. Also, it's not hard to show that for this entire family of protocols, there's quite a simple upper bound you can derive on the highest possible noise tolerance in the depolarizing noise model. And you can see that we're actually pretty close to it. So the results of this work are really pretty close to the best possible result you could hope for this entire family of protocols. And there may not be much scope in further improving the results. Okay, but this was for the simple noise model of depolarizing noise. And let's move on to how it looks in the setting of the existing bell test experiments. So first of all, as expected, because the individual protocol variations were already able to achieve positive asymptotic key rates, so by combining them, we were also able to achieve positive asymptotic key rates for essentially most of the existing bell test experiments, at least in theory. But we were also able to gain some insight onto which of the protocol modifications contributes more in each of the existing Bell experiments. So for example, for the NV center and coal-atom implementations, it looks like most of the improvement we can achieve comes from using the random key measurements technique. You can improve the key rates a little bit more by using noisy preprocessing, but only by a fairly small amount. On the other hand, for the photonic model, it was a bit more challenging to analyze. We found that there were many parameters that you can optimize in the experiment. And in this work, at least, we were not able to find improvements in the key rate beyond those that were achieved using only noisy preprocessing. But this isn't to say that it's impossible. It's just that we were not able to find parameters that improve the key rates beyond this. In fact, in light of the extremely recent results that I mentioned, there's some developments on this point, which I'll mention in more detail at the end. Moving on to part 2 of our work, this is the finite size analysis, since we have now shown, or we now know that the existing Bell test experiments can achieve positive key rates asymptotically for the DIQKD. And our finite size analysis is based on a result from a few years ago called the entropy accumulation theorem. The powerful aspect of this theorem is that it incorporates finite size and non-IID effects, and it was already previously used to develop a security proof for the basic DIQKD protocol. Our contributions in this case were that, first of all, we modified the security proof so that we will be able to analyze a protocol that combines all of the variations that were developed. We also made some modifications to the security proof that resulted in tighter finite size bounds, as well as accommodating some practical protocols in a few classical steps, such as the error correction step of the protocol. We also made a proposal for a protocol modification based on a pre-shared key, which is essentially intended to mostly help the random key measurements technique. Roughly speaking, it essentially ends up doubling the net key generation rate for the random key measurements technique because it removes a sifting factor that appears when applying the basic proposal for that approach. But without going into details of the finite size analysis, I'll just present the results that we obtained. Here for this slide, we can see the results that we obtained for the NV center Bell experiment and the coal-atom Bell experiment. And on these graphs, the different colors are the finite size key rates as a function of the number of protocol rounds, and the different colors represent different security levels, so to speak, different choices of security parameter. But since you can see that the differently colored graphs are all not that far apart from each other, they're pretty close. This indicates that choosing different levels of security in the protocol doesn't really affect the finite size key rates by all that much. I mean, you can see there is some change, but not all that much. The main difference that I want to focus on is that the solid lines here show the finite size key rates that we can achieve with security against non-IID attacks by the adversary. On the other hand, if we restrict the adversary to only IID attacks, we get the dashed lines over here. And we can see that there's not all that much difference between the IID and the non-IID case either, indicating that the security proof here should be fairly tight. Unfortunately, the results look a bit pessimistic for implementing the DIQKD using these experiments because the required sample sizes to achieve a positive finite size key rate are still fairly large. Even if you modify the protocol a little bit to optimize it for the IID case, the required sample size for the protocol is still pretty large and it doesn't help all that much. It's a bit impractical for these experiments. On the other hand, we haven't covered the photonic experiments yet, and for that situation, we have a challenge to overcome as well. So if we go back and look at the graph of the asymptotic key rates alone, remember that I mentioned the threshold at which the key rate goes to 0 is about 82.6%, and this is more or less within reach of the existing photonic implementations. The problem, however, is that the asymptotic key rate becomes extremely low when we are near to this threshold, and because of this, once you account for finite size effects, the key rate goes to 0. So this is a challenge that we have to overcome. The good news is that just a couple of months ago, there were 2 papers that released better methods to compute the asymptotic key rates as compared to our approach. They are more efficient and more numerically stable. Using these methods, they were able to show that for some simplified models of photonic experiments, the threshold efficiency can be lowered further to 80.26%. And more importantly, however, the key rates are pretty high even when near this threshold. So this helps make the key rates more robust against finite size corrections. And because of this, it might be possible to implement a finite size demonstration of the DIQKD using photonic experiments. Of course, now this raises some very interesting points to work on because first of all, these results haven't performed a finite size analysis yet. So we would be very interested in performing a finite size analysis using entropy accumulation. And the other point is that the photonic model considered in these works is a somewhat simplified one, and it will be interesting to study a more detailed model for the photonic experiments. So to sum up, today the results that I would like to have presented is that first of all, we have this method for computing the key rates for protocols based on a tilted CHSH inequality. Our results are quite similar to the preceding independent work. Secondly, we also have a method for computing the key rates for protocols that combine all the variations that were proposed. And using this, we obtain a new threshold on the depolarizing noise tolerance. We also made some improvements to the finite size analysis and compared it to existing bell test experiments. Looking forward, our results show that the anti-center and cold atom bell tests would still need significant improvement in the experimental parameters if we want to try and do a finite size DIQKD demonstration with them. But on the other hand, the photonic implementations, given the very recent results, they look quite promising. We just need more detailed analysis regarding a more precise photonic model, as well as performing a finite size analysis. Another topic in the DIQKD that seems to have attracted interest in the past few years is the question of upper bounds on the key rates. So it's a sort of converse task to what we are trying to solve here. And if we want to bring the key rates closer to match these upper bounds, it might be worth considering protocols that go beyond all the ideas that I've talked about in this work, because everything that I've described in this work is for protocols using one-way communication for the DIQKD. But the DIQKD protocols based on two-way communication might be able to achieve higher key rates, and this is an idea called advantage distillation, which we have a poster that we are presenting on this later on in the poster session. And overall, it looks like the outlook for the DIQKD seems fairly promising, and it might even be possible to do a photonic experiment to demonstrate the DIQKD in the near future. And yeah, this marks the end of my talk. I thank you for your time, and I'll be glad to answer any questions you might have.